Let us quickly review what we have done so far in line coding. What we have learned so far in line coding. We have seen that if we do simple on-off kind of signaling, we get this kind of power spectrum, right? That you may recollect, which contains both a continuous part as well as a discrete part. In addition, we notice that the bandwidth of this is 2f0 if you consider the main lobe width as a bandwidth, right? I'll only summarize here and not go through all the things that we discussed about various line coding schemes so far. Next, you may recollect that we considered the polar and the bipolar cases, and the kind of power spectrum for the transmitted pulse sequence that we obtained looks like this for polar, which has the same bandwidth as the on-off signal, that is 2f0, but it does not have the discrete spectra that displayed, right? Plus it does not have that strong DC component, impulsive DC component that was also present in the on-off signaling. The bipolar case, in which we did alternate Mach inversion, if you may recollect, and in which we have a 0 represented by a 0 level, no signal, no pulse, and a 1 represented by PT or minus PT, right, has this kind of a spectrum, which has surprisingly, well, not that surprising after we looked at the spectrum, a bandwidth only of f0, which is half that of 2f0. But you may recollect my telling you that even this is twice the theoretical minimum that we can have, and therefore its bandwidth efficiency cannot be said to be very good. Alright, and we like to see whether we can improve on this bandwidth efficiency further by other kinds of line coding schemes, right? And that's what we'll start with today. These are the three schemes we have discussed so far: on-off signaling, polar and bipolar. Have we discussed anything else? I think that's what we have done. Now I'll introduce to you first yet another new scheme which we haven't discussed so far. We'll come to HDB3 or HDBN a bit later, but before doing that, I'd like to introduce to you a new line coding scheme. New to you, I mean. It's not really new in the context of historical evolution. It's fairly well known. That's called duo binary signaling. Okay. This line coding scheme is particularly important because we'll see that it helps us to achieve a bandwidth efficiency which is equal to that of the theoretical minimum that we can expect, right? This was originally proposed by Lender. This is a very famous name in this particular line coding schemes in 1960s. Okay. This is also a ternary scheme or a pseudo-ternary scheme of the kind that we use for bipolar signaling. So it is also pseudo-ternary. That is, we use no pulse for 0 and PT or minus PT for a 1. But the difference is, as against the bipolar kind of signaling that we have done before, namely the AMI kind of signaling, the bandwidth required is only half of that. That is, instead of 2f0, we will require a bandwidth of f0 hertz. Instead of f0, we will require f0 by 2 hertz, which is half that of bipolar. The basic scheme is as follows in duo binary signaling. I have already told you 0 transmitted by transmitting no pulse, right? 1 represented by a pulse of shape pt or it's negative. Now whether you transmit pt or minus pt, this depends on the polarity of the previously transmitted pulse, number 1. So depends on polarity of previously transmitted pulse. So previous pulse, that is one thing that determines what will be transmitted next. Also it depends on how many zeros have elapsed between the previously transmitted one and the one that you are doing now. We don't actually count the number of zeros, we are only interested in knowing whether the number of zeros is even or odd, right? So for example, if the two ones, that is the previous one and the current one, are separated by an even number of zeros, we transmit a pt, otherwise we transmit a negative pulse. Alright, so it depends on number of zeros, more precisely whether it's an even number or an odd number between the two pulses, between the two ones, two successive ones. Alright. Okay. Any questions about it? The basic scheme is clear. So let me take an example. Let us say, maybe I have it somewhere. Yes, I have it drawn here. Let's say that's your transmitted sequence that you want to transmit on the channel. Now in the dual binary coding scheme, this will be a 1. Each interval here is like that. Okay, this is one transmission interval for 1 bit. So obviously, since the two ones here are successively same, there is no zero in between them, which indicates an even number of zeros, because we will consider 0 also to be an even number. Then the polarity remains the same. Same is true here, and zeros are transmitted by transmitting no pulses. Since we have 3 zeros in between this one and the next one here, the polarity is reversed. And now again we transmit with the same polarity till we get an odd number of zeros again, right, which is the case here. So we keep on reversing the polarity depending on whether we have an odd number of zeros between two consecutive ones or an even number of zeros, right. That's it. Okay. Here we have even number of zeros, so we transmit this same polarity. Again even number, same polarity. Even number, same polarity. Odd number, odd number. Reverse the polarity. Okay. Let's look at the power spectrum of such a scheme. Let's do a computation of S, Y, omega. And if you may remember, the steps required are to compute the RNs, right? That is R0, R1, R2, etc. R0 will be determined by sigma AK square, right? Now AKs are 0 for half the time and either +1 or -1 for half the time, right? Because we are assuming again that AKs are the original data sequence contains zeros and ones with equal probability, alright? So in any case we are interested in AK square, so AK square will take the value 0 or 1, right, each with probability half. Same here. Okay, which makes it clear that R0 should be equal to half, 1 by 2. Why 0? It should be, if you remember the expression, T0 by T into the number of values of 1 that you will get in AK square, because you are looking at sigma AK square over K, those indices K which lie in the interval from minus T to plus T, that will become T upon 2T. Half of the pulses, half of the symbols in this interval will contribute a 1 here in this term, and therefore that is the value that you will get, half. Consider next the value of R1, which will be determined by sigma AK plus 1, right? Therefore, let's concentrate on the behavior of, or the values of AK into AK plus 1. It's clear that
1 minus 1.
okay, it's quite clear. Each of them will contribute a non-zero value only if they are both non-zero, right? That means AK should be plus minus 1 as well as AK plus 1 should be plus minus 1. And from your elementary knowledge of probability theory, if we assume that these two symbols are emitted independently of each other, the probability of this to be non-zero and equal to 1 or minus 1 will be 1 by 2.
1 by 4 each will be the probability for being non-zero.
Okay. I said probability of its being either 1 or minus 1 is 1 by 2, but probability of its being either plus 1 separately and minus 1 separately will be 1 by 4 each, right? Of course, these two are exclusive events, that is why they sum up to half.
No sir, it's either 1
by 4 for what?
The probability of it being either plus 1 or minus 1 is 1 by 4.
Sir, the point is this. So we can have
Oh yes,
four
yes,
sequences.
yes, absolutely right. You are absolutely right. I made a mistake. Let me elaborate for the others. Those who have said this have said it correctly. Probability of AK equal to plus minus 1 is equal to half. Similarly, probability of AK plus 1 equal to plus minus 1 is equal to half independently of each other, right? And therefore, the probability of both of them being non-zero will be equal to 1 by 4, the product of these two, right? So, we can say that AK into AK plus 1 is equal to 1 for only.
So is it independent of AK?
Both are independent, yeah.
So because once
We are assuming that is an assumption that successive values of binary symbols that are being emitted by the source are being emitted independently of each other.
So but in this case, if you got AK equal to 1 or
Yes.
minus 1, in the next
I'm not talking of the coded value. I'm talking of the original symbol value,
okay.
right? The coded values depend on each other, right? So let me put it this way: AK into AK plus 1 is equal to 1 for only half of those cases for which AK is equal to plus minus 1 and is equal to 0 for the other half, right? In any case, what is really important is the fact that the probability of this being non-zero is 1 by 4, right? That is what is really important. Then what is the value of R1 then? It's 1 by 4, right? Because if you start with plus 1, right? I think it may not be clear to everybody. Suppose, no, I thought there was still some confusion, so I should resolve it really. Let's do it here. If AK is 1 or plus just a second. We are looking at AK into AK plus 1, and suppose we start with AK equal to minus 1, right? Then we can have the combinations minus 1 and minus 1, which will contribute to a non-zero value. Similarly, minus 1 and 0 as the zero value, right? Similarly, we can start with AK equal to 1 and 1 and 1 and 0, right? So we are talking of 1 and 1 I have taken, 1 and 1, minus 1 and 0, and 1 and 0. Alright? These are the 4 possibilities. So what you see is, out of these 4 possibilities, which occur with how much probability? No, each is not 1 by 4. Each is 1 by 8. Because we are assuming this starting bit to be either minus 1 or plus 1. We are not permitting this to be 0. Right?
Can be 0, 0 is possible, sir?
You can, but they will all contribute 0 with half the probability. Right? So this total sequence has probability half. Right? And therefore the probability that you will get a non-zero value will be 1 by 4, which is what we considered earlier. Not only that, what we notice is that this non-zero value is plus 1. Right? It cannot be minus 1. That is why R1 has to be equal to 1 by 4. Okay? Is it clear? Because AK can be minus 1 or plus 1. For AK equal to minus 1, AK plus 1 could be either 0
Or minus 1.
or minus 1 here. Right? Okay? And similarly here. I'm sorry, I don't know whether I have confused you. Please let me know if it is okay.
It's alright, sir.
Okay, now people want me to repeat, I'll do it.
So initially you said you're not considering the encoded value, you're considering only the original signal. Now if you're considering the original signal, why can't you have the value like minus 1, 1?
Minus 1, 1 cannot be there.
Okay, let us consider this question. Why we can't have minus 1 plus 1?
There's not possible.
And not possible.
There's an even number of zeros in
Doesn't say 0, only says 0
Where do you
is
consider the encoding?
So you're considering the encoding.
Independent of encoding.
There is a question of minus 1.
I think I am also slightly confused here. Just give me a second.
If you don't consider encoding, where is minus 1 coming with also?
Okay. All right. Let me repeat it. This point. We start with the point that we have as. Let's start with the point that AK can be equal to plus minus 1 with probability half. Right. So we are ignoring here the value AK equal to 0 because that will not contribute to the product. The next value, the next point is what kind of values can we have for AK plus 1, right? Now the dual-binary rule says that AK plus 1 must be either of the same polarity or of the opposite polarity or 0, right? These are the three combinations, right?
It cannot be of the opposite.
So, but in this case, it can't be of the opposite polarity.
Because we AK plus 1.
Plus 1.
Because we are talking of AK plus 1,
When
right?
AK
The number of zeros here is even. So they have to be of the same polarity. If you follow the dual-binary rule, two successive bits have to be of the same polarity. We have already seen that by the example over here, right? Because two successive bits are 1, they have to be of the same polarity. They have to be either they are both negative or they are both positive. That is why we did not consider the probability of this being minus 1 and plus 1, because that is not possible. Similarly, we can't have plus 1 here and minus 1 here, right? So these sequences are not possible. Now this total number of these 4 combinations occur with probability half. Therefore each of them occurs with probability 1 by 8, out of which only 2 of them will contribute a value to the product AK into AK plus 1, and that product value in each case happens to be plus 1, right? And that is why R1 turns out to be 1 by 4. I hope that is clear now.
So when AK is 0,
Yes.
there are only 3 possible values of AK plus 1. 1, minus 1 and 0.
It doesn't matter what it is.
So no, what I mean to say there are total 7 possible values because there are
No.
possible pairs. So how can the probability 1 by 8 of each?
No. Please. We are just using very basic elementary probability theory here, which says that probability of AK and AK plus 1 together, the joint probability, please listen to me, the joint probability of these two is right, out of which we are taking this to be
These are independent.
right. No, if they are independent, this just simply becomes
Yes sir. So I am not saying yes. So what I am saying is there are total 7 pairs possible, not 8. As you were saying that there are 8 pairs possible. Therefore, it's see when AK is 0.
no. I was talking of I didn't talk of any 8 pairs
So because
anytime.
you said the probability with when AK is 1.
We are considering, please try to understand, AK can be 0 or plus minus 1. What is the probability of that? Half each. Either 0 or plus minus 1 will be half each, right? Now given that this event is occurring with probability half, this 4 set of events must have a total probability of half, right? That is the point that is being made. And therefore, assuming equally likely situations here, we have 1 by 8 here and 1 by 8 here. Okay, together they add up to 1 by 4. So our starting premise is that we are assuming AK to be non-zero, which has a probability half, right? Okay, I'm sorry for the confusion, but I hope it is resolved now. All right? Okay, we proceed further. Similarly, I think I'll leave that as an exercise because apparently we are causing a lot of problems here counting zeros and ones. I think you can do that at leisure yourself. It is comparatively easy to prove that Rn for n greater than 1 is 0. Okay? Please think about it yourself so that we don't have any more confusion in the class at least. Okay? It's very easy to prove that. If you now make use of these results, that is R0 is equal to half and R1 is equal to 1 by 4, and substitute in the expression for Sy omega that we have earlier with us, which is this, we get this result. Okay? Do I have to show you that expression again, or it's okay? All right. Let's simplify that further. 1 plus cosine omega t0 can be written as cosine square omega t0 by 2 divided by multiplied by 2. So this will become p omega mod square upon t0 into cosine square omega t0 by 2. Okay? Now if we consider a specific pulse shape like we have been doing, remember the pulse shape that we have been most commonly using for comparison purposes is the half width rectangular pulse. So we'll come back to that again, that is this particular rectangular pulse. Then we get that sinc square function for p omega mod square, and the result is t0 by 4 sinc square omega t0 by 4 pi into cosine square omega t0 by 2. Yes, please.
So the writing is a bit small. Could you
It's still small? Okay, I'm sorry. I'll try to. The brightness is small. Other writing is small.
brightness is
Okay.
less and the letters
Okay.
are also very small.
Okay, I'll try to write them big. Please remind me whenever I forget that. Huh?
That should do with the illumination.
Everybody can see them. They're too far away for the back to.
Let's discuss these suggestions at the end of the class. Okay, if you don't mind. At the moment, I think I'll try to write bigger so that you can see it better. Okay, let's return to this expression here. Is there some other problem? Let's return to this expression here, which is the power spectrum of a duo-binary coded scheme, duo-binary coded data signal. All right. Now, the first thing we note is that it has a 0 at where do we have a 0? Sy omega equal to 0 at omega equal to pi by t naught, right? Because at pi by t naught we will get pi by 2 cosine of pi by 2, which is 0, right? So that is interesting. That is, our first 0 crossing in the spectral plot will now be at f naught by 2, not at f naught, right? So far, all the spectral shapes, all the pulse shapes we discussed have their first 0 crossing actually determined by the sinc square function, right? We did have a multiplication factor in some other schemes, but the first 0 crossing always came at either f naught or 2f naught, right? Not at f naught by 2. This is the first scheme we are saying in which the first 0 crossing is occurring at f naught by 2. So we can expect the main lobe to have a width of f naught by 2 on either side of 0, and that's precisely what I have got here. You can see the plot. This is your duo binary scheme.
There are two.
Yeah, I'll show you which is the one. We are considering duo binary with half pulse width, right? That is shown by these dotted lines here. I think I'll write with a different color so that it becomes clear which is the one I'm referring to. That is your duo binary scheme. Okay? Its first 0 crossing is at f naught by 2, and the next one occurs at 3 f naught by 2. This is duo binary with half pulse width, right? This was your bipolar thing, which was occurring with which has its first 0 crossing at f naught, right? And this is the duo binary case.
So for the black one,
There,
it is not occurring at, it is occurring at 2 f naught, even f naught rather, isn't it?
well, I'm telling you, this is the duo binary scheme spectrum, right? This comes from this expression here that we just derived. Yeah, it's here, right? This expression here, sinc square function multiplied by this cosine square function, right? That turns out to be this, because we get our first 0 crossing over here. Now, although it seems therefore that we have achieved what we wanted to achieve, there is a small problem you can notice. The second lobe is not all that small as compared with the second lobes of, let's say, the bipolar, right, or other schemes that we have seen earlier, or the polar, right? Therefore, it seems that significant energy still seems to exist between f naught by 2 and beyond, right? However, that is not a very serious problem. Why? Because we have only used one of the things at our disposal, right? Namely, the control. We have tried to control the spectral shape by the coding scheme only so far. We can as well also control phi omega the pulse shape, right? Just to show what kind of things we can do by controlling the pulse shape, we'll discuss that in detail later, soon after we discuss the basic line coding schemes. Here I have plotted here the duobinary scheme spectrum when you take the pulse not to be the half width pulse but the full width pulse. And what do we notice now? Now this black solid line indicates the spectrum in this case. The solid line spectrum drawn here is the spectrum of the duobinary signal with a full width pulse, that is a rectangular pulse of width T0. Alright. What we find is that the side lobe levels have considerably got reduced and the main lobe width remains the same. Right. The point that is being made here is not that you should use a full width rectangular pulse, you may or may not use, but the important point is that one can control the side lobe through a proper pulse shaping of PT. Right. You don't have to use the rectangular pulse of half width. We can use some other pulse shape and then control this lobe and therefore maintain the bandwidth essentially in the region f0 by 2. Okay. Alright, so that is as far as the spectrum of a duobinary coherent signal is concerned.
Other things are there, it's semi-transparent to...
We'll now come to the other points. Let's discuss the duobinary scheme in some more detail now. This is only the spectral aspects of it. Can you read this alright? Or you want still bigger? Okay. So first thing we have learnt just now is that the bandwidth of a duobinary scheme is half that of bipolar. Alright? Considering only on the main lobe basis, and that is the only important thing because we can always shape the side lobe or the second lobe down by appropriate shaping of the pulse. Now the other properties of the duobinary scheme are essentially the same as that of the bipolar scheme that we have discussed earlier. That is quite clear because like the bipolar we don't have a concentrated component at DC, right? We don't have a net DC level, right? DC values are, because of the fact that alternating pulses are on the whole equal number of pulses are likely to be positive as negative, right? So we have more or less similar properties to that of bipolar, except for one fact. Can you say which one is that?
DC.
Right. We don't have a spectral null at omega equal to 0, right? Except for a missing spectral null, which was very useful if you remember. So like bipolar, we have a 3 dB disadvantage with respect to what? 3 dB disadvantage with respect to a polar scheme, right? That is for the same performance, either the bipolar or the duobinary scheme, because they are ternary schemes, they are both ternary schemes or pseudo-ternary schemes, will require 3 dB more power than the polar scheme. So with respect to the polar signaling scheme, like the bipolar, that is the AMI kind of scheme, we also have error detection capability. Which is quite obvious, right? Because if two successive pulses come with the same polarity and an odd number of zeros between them, we can deduce that there is an error that has taken place somewhere, right? And similarly the other way around. So all the properties that we have seen for bipolar are valid for duobinary, with the added advantage that the bandwidth is only half of it. right? And the disadvantage that there is the spectral null that the bipolar had at omega equal to 0, right, at this point is missing. So these are the main features of a duo-binary signaling scheme. Later, Lender himself, you remember Lender was the person who introduced the duo-binary scheme. He himself came up with a so-called modified duo-binary scheme, which eliminates the disadvantage that it has with respect to the bipolar. That is, which has a spectral null at omega equal to 0. This seemingly simple modification that is inherent in the duo-binary scheme with respect to AMI kind of schemes, and after its modification to introduce a spectral null at omega equal to 0, made it a very, very useful device, useful coding scheme. In fact, soon afterwards, companies came up with systems which could take two basic units of the T1 carrier system of the US time division multiplexing standards, which each contain, if you remember, 24 channels, voice channels, and combine them into a single system with 48 channels with the same bandwidth, right? So one could build repeaters which could transmit 48 channels, 48 PCM channels. Now we are talking in the American context because Lender was an American and he introduced this scheme there. We could introduce 48 we could use 48 PCM channels over the same bandwidth that was earlier being used for 24 channels. That shows the significance of choice of proper line coding scheme, right? One has doubled the bandwidth efficiency. There is a doubling of bandwidth efficiency here. Which is very, very significant.
For the duo-binary or modified duo.
Well, even duo-binary has the same advantage, except that there is the spectral null at omega equal to 0 is missing.
What is the modification?
We'll discuss that later, right? I'm not discussing the modified duo-binary here. We'll discuss it in a slightly different context later, right? I just wanted to introduce to you the duo-binary concept here, which is essentially a small modification of AMI in some sense. Next, let us come to yet another line coding scheme, which follows a slightly different philosophy from the one that we have discussed so far. In all the line coding schemes from bipolar onwards that we discussed so far, we have tried to do the spectral shaping essentially by controlling the manner in which ones and zeros are represented, successive ones and zeros are represented by actual signals, actual pulses, right? We are not really bothered. We are not done so much with the pulse shape itself. We could also do that, and that leads to one more kind of pulse shaping that line coding scheme that we will just briefly discuss here, which is known by the name of split phase or Manchester coding. You may be familiar with this coding scheme. So the point that I am making here is we have noticed that we can split our SY omega into two parts, namely a part which is contributed by the pulse shape and a part which is contributed by the impulse train with amplitudes, random amplitudes ak, right? Sx omega denotes the power spectrum of the impulse train. P omega mod square indicates the power spectrum of the pulse shape that you use. So one can do spectrum shaping not only by just controlling Sx omega but also by controlling P omega, right? In particular, suppose our primary requirement is to introduce a spectral null, right? Let us ask the specific questions. Can we introduce a spectral null by controlling P omega or Pt? It's very easy to see that yes, we can. P omega is the Fourier transform of the basic pulse shape Pt, which is this. As far as the DC value is concerned, that is the value which is determined by the area under the pulse, right? Because you put omega equal to 0, this vector disappears. So P0 value is essentially determined by the area of the pulse. So if you can choose a pulse shape such that the net area under it is 0, we'll get a spectral null, right? And Manchester coding is one example of a split phase coding, or Manchester coding is one example of precisely this kind of coding. So your PT is determined by this requirement. Oops, I'm sorry, this is right. Let me read right. So this is your time axis. Half the interval of the pulse width, the pulse is having a positive amplitude, let's say +1, and the other half it is having a negative amplitude, which is -1. So the overall interval t0 is split into both a positive portion and a negative portion with equal areas, so that the net area under the pulse is 0. And the mapping that you may do, and that is what Manchester coding does, a 1 represented by Pt and a 0 by -Pt. This is known by the various names split phase, Manchester, and also twin binary. Various names for historical reasons.
So for 0 current we have simply 0 level instead of -Pt.
For various other reasons, we will like to have this way. That is what Manchester coding does anyway, right? One can always define a new line coding scheme, right? We are suggesting one more, but we'll have to study what the properties of this are with respect to Manchester coding and see whether it's worthwhile adopting or not. But this is what you do in Manchester coding. Now, as far as power spectrum of this is concerned, that is very simple. Essentially, what kind of signaling we are finally getting? If you just look at it, if you just look at the final pulse sequence that you will get, what kind of sequence will it be? Will it be ternary or polar? Will it be bipolar or polar? Polar, right? It will be polar, and we have already discussed the power spectrum of a polar signal, right? If you remember, for a polar signal, power spectrum is simply this. For equally likely ones and zeros, the second factor completely disappears. We have already done this in the last class, right? So recollect that for a polar signal, the power spectrum is given by this expression. Yes, please.
I don't understand the 0 -Pt and 1 Pt part. Can you explain that again? Like what correlation does it have with the fact that the area of Pt has to be 0?
No, this is just a mapping. Both of these will have 0 area. We want both pulses to have 0 area, right? Both the pulse which is being used for representing a 1 and the one which is being used for representing a 0, right? And PT and minus PT will both have area 0. That's what we want. Okay? So this is the power spectrum. Any questions? Any other question? Any other doubts?
This will be different from the thing which you discussed just now. This duo binary.
This is quite different.
Altogether different. I mean,
Yes.
we don't have the alternate.
No, there is no further coding rule here.
That's all.
Right? It's just a mapping of 1 and 0 which is done in using this particular kind of pulse shape. The whole idea is that I'm now controlling Sy omega not through control of Sx omega, which is what was being done in all those coding schemes, right? But by simply changing my pulse shape, right? One can do some combinations. One can do both a control over PT as well as over Sx omega. There's nothing stops us from doing that. Yes.
What if it is almost similar to the polar steam?
There are similarities, and that's why we are saying that the power spectrum is given by basically the same expression, but there is an important difference. P omega is different, right? P omega is different, and if you substitute for P omega, to do that, let's write down an expression for PT. This is actually composed of two rectangular pulses of opposite signs, polarity. So mathematically, I can write this as a rectangular pulse, let's say between minus t0 by 2 to plus up to 0, which you can think of as being located at minus t0 by 4, right? So t plus t0 by 4 of width t0 by 2. Width is t0 by 2, right? Minus a rectangular pulse which is located at t0 by 4 and has the same width. Okay? Fine? Once I have this, we can compute P omega without any problem. What will be P omega? It will be that sinc square function corresponding to a pulse width of t0 by 2, which we already know, except that it will have a multiplication factor of e to the power minus j omega t0 by 4, and this will have plus and this will have minus, right? So your P omega is t0 by 2 sinc function with a parameter omega t0 by 4 pi corresponding to rectangular pulse of width t0 by 2 into e to the power j omega t0 by 4 minus t0 by 2, again the same sinc function omega t0 by 4 pi e to the power minus j omega t0 by 4, which you can factor it out. The sinc function can be factored out. You will be left with e to the power j omega t0 by 4 minus e to the power minus j omega t0 by 4 upon 2, right? Which you can write as 2j t0 sinc omega t0 by 4 pi into sine omega t0 by 4.
So it should be JT0. Yes,
2 won't come, sir.
Right. This will be simply j t0. So your Sy omega in fact will be this whole square, magnitude square of this upon t0, and this will become t0 sinc square omega t0 by 4 pi into sine square omega t0 by 4, which shows clearly that there is a spectral null at omega equal to 0 because you have multiplication by sine function, right? What is the bandwidth of this spectrum, this signal? Where is the first zero crossing? Main lobe width is?
F dot.
Same as bipolar.
2f naught.
F naught. Right? Because of this. right? So bandwidth is, I'm sorry, you're right.
2f0, sorry.
Now where is the next zero of this?
This will be omega equal to 440 naught.
Omega is equal to 4 pi.
2
Omega
pi.
equal to 230 naught.
This will be at 2 pi.
230 naught.
2f. This will be at 2f naught, sir.
Right, it is at 2f naught. Okay, I'm sorry. So bandwidth is twice that of bipolar. And that is understandable, right? Can you see why? Because you're always bound to have zero crossing at every t0 by 2 seconds, right? So effectively, as if your average rate of bit transitions has gone up from every t0 second to every t0 by 2 seconds, right? Therefore the bandwidth is doubled. Okay, so it makes sense to expect the bandwidth to be doubled with respect to the bipolar scheme. So we are back to the bandwidth that we used in the unipolar scheme, right, with rectangular pulse shapes of width half. So that is shown in this diagram as far as bandwidth is concerned. This was your polar scheme, just to put everything in a proper perspective. This was your polar scheme spectrum. Mind you, it might give the impression that the spectrum is zero beyond this. Please remember, it is not, right? However, we are mainly concentrating our attention on this portion of the spectrum, that is the main lobe portion of the spectrum. For bipolar, we get our first zero crossing at f0 instead of 2f0. For split phase, once again we get it here. So it has some advantages with respect to at least the polar case, in the sense that we have a spectral null at 0, just like the bipolar one does, right? But the bipolar spectral null was obtained by coding. The Manchester spectral null is obtained by pulse shaping, right? That is the essential difference. Now, so is there any possible advantage of split phase over bipolar whatsoever? It seems that we already have seen that its bandwidth is certainly not very nice, not very interesting. It's twice. 3 dB advantage. Yes, that is there.
Yes, 3
dB advantage is there. It has the same properties in that as polar is concerned. But there is one more advantage it has, and that is, if you look,
long string of zeros and ones.
That's right. It will be absolutely transparent to long string of ones and zeros, because no matter whether you are having a zero transmission or a one transmission, you will always have a change in. There will always be a transition from 1 to -1 and -1 to 1 because of the peculiar shape that we have used, right? Because of this shape of the pulse, there is guaranteed to be a transition, right? So any scheme which is Manchester coded, any data sequence which is Manchester coded, will be transparent to long strings of ones and zeros. So from the point of view of timing extraction and synchronization, it's a good shape to use if bandwidth is not a constraint. If bandwidth is not a consideration, in some applications it may be so, one can consider Manchester seriously because of this convenience that it gives you. Alright. But except for this fact, generally its other properties are not very desirable properties, particularly the bandwidth one, and therefore one has to be careful before using it. Yes? This word I am just using a bit casually. It means that it doesn't matter if there is a long string of ones and zeros. We don't lose our timing synchronization, because we have discussed it earlier. If we get a long string of ones and zeros, there is a distinct possibility that we may lose our synchronization for some time momentarily. We'll have to acquire synchronization again. We'll have to make sure that our loop gets back into synchronization fast as soon as this phase disappears, right? If on the other hand we have we don't have this problem, then we say that we are transparent to whether the data sequence is of this type or that type. it doesn't really matter to us.
So this part was not very clear. What do you mean by losing synchronization? Is it long string of 1 0
I have not, the reason it may not be clear, although I did try to mention something about it, is that we have not yet discussed any synchronization scheme, right? But the essential fact in any synchronization scheme is that it has to derive timing information, clock information from the received data, right? And the clock information, roughly you can imagine, will be contained in the zero crossings or bit transitions, right? The more the number of bit transitions you have, the more regular the bit transitions you have, the better it is for the timing recovery circuit, right? If on the other hand, for a period of time, these bit transitions disappear for whatever reason, because of the kind of data that is being transmitted, you'll have problem in extracting the timing. That is what we meant, right? That is why long strings of ones and zeros are not good from the timing extraction point of view. So unless we can make our coding transparent to this, right? That is, it shouldn't matter. Even if we have long strings of ones and zeros, we continue to get zero crossings or bit transitions.
It will be difficult to get a clock in it.
That's right. It will be difficult to recover the clock from the received signal, which is important for carrying out the demodulation functions, decoding functions. Okay. Let's next come to HDB coding. Time is up. Okay, I'll just take a few minutes, I think. Let me complete this because I won't be really going to the details of this. If you will be kindly patient for a few more minutes. Okay, why I'm not going to take much time is because I'm not going to take the spectral calculation of HDB coding in detail. The reason is it is very involved. Okay, that's why I'm not going to do it here, and therefore we can cover this topic quickly and finish off with this. Now, basically, what turns out is that if you try to do the spectral analysis in the manner that we have been doing so far, there are other methods of doing spectrum analysis which we have not discussed, right? But the one which we are discussing requires us to calculate the autocorrelation coefficients Ri's over whatever period they exist, they are non-zero, right? Once they become non-zero, we are okay. Then we can go ahead and do the calculation. But it turns out that for doing this for HDB coding requires you to calculate RNs for very large values of n. Right? As an example, if you were to consider HDB3 coding, which is the simplest to analyze because n is 3, you need to go up to n equal to 63. So you need to evaluate R0 to R63 to be able to compute the spectrum, because it doesn't become 0 before that, right? Or it doesn't become small enough before that. If it doesn't become 0, it should at least become small enough to ignore, right? So it so turns out that you require a very large number of terms in that spectrum calculation to be able to compute it reasonably accurately. But obviously such computations have been done and results do exist, and I'll just give you a feel for the HDB spectrum with respect to the bipolar spectrum. Suppose both of them, if you remember, well, bipolar, if you remember, has a spectral null at the first zero crossing at f0, right? So does HDB3. This is HDB3. This is bipolar. Okay? So as far as the main lobe width is concerned, they are the same, but there is a slight difference in detail in terms of the actual shape of the spectrum and its concentration in the main lobe, right? Except for that difference, they are really very similar. Okay, so I thought I'll just tell you this and mention the fact that HDB3 also has the same error detection capability as bipolar does, right? In spite of the fact that we violate those inversion rules, right? We get after 3 zeros, we transmit a 1 with the same polarity as the previous one, rather than the opposite polarity. Can you imagine why we can still use error detection? Use this kind of scheme for error detection? Because suppose there is an error. What will it do? It will either delete a violation that we have carried out, or it will introduce a violation of its own. Right? These are the two things it can do. Now, each of these facts, you can satisfy yourself, will be detected at the next violation point, where we expect, where there should be a violation. You will find it does not exist.